What I'm about to talk about is a concept of manage anything, which means I will do a quick stroll to controlling code or software that is running outside of OSGi, managed by OSGi, maybe on the same machine, maybe even beyond that. What we will find in here, well, short introduction. I will hog some of the terminology used, but I think that is no magic for you. Quickly strive through related technologies, and then speaking about an approach that we have developed at ICAS to manage code outside OSGi with OSGi. So I don't know whether you have heard about ICAS yet. If not, here are some company presentation on what we are and what we do. So we started our company around a real-time capable Java runtime. And then we actually have an ahead-of-time builder tool, which has the functionality nicely described in the talk before. We have put an application management framework on top of it even before we entered OSGi. Nowadays, it's OSGi-based. And now we start to provide web tools, cloud-based tools, to control all of that remotely. I will get to that a little later. We are quite successful with that, deployed to some companies with big names. We are pretty big in an American automotive OEM. So we have 20 years on our counter now and over 25 million instances of our runtimes running. Who's me? I have started at ICAS kind of 10 years ago, or pretty exactly on the day, 10 years ago, as a developer in a project with German Tier 1 for quoted US automotive OM. So we were starting to develop the Stellantis Uconnect system in there. I grow, becoming project manager, product manager in there. And as of now, I'm the head of product and solutions architecture at ICAS. Into the terminology. I will use the word software component quite a lot, which is anything in any language that can be executed by a runtime specific to that language. Runtime in a second. And those software components usually are managed in software component life cycles, which is not exactly a product life cycle, but rather the life cycle that is executed at runtime. It's not even DevOps, though it integrates in the DevOps loop. So when I reference software component lifecycle, I always speak about downloading something to a remote target system, maybe installing it into some framework there, resolving dependencies if it's OSGi, then powering the whole thing up, and vice versa, stopping it, uninstalling it, deleting it from the platform. Runtime is the execution environment for those software components. Well, basically, a runtime for me is everything from operating system, from bootloader even, to interpreters, to container runtimes, to specialized runtimes for, e.g., ML models, to specialized runtimes, which is hardware like the ESP32 I put onto the slide for executing some kind of software. Oftentimes, those runtimes have some more characteristics to it, like e.g. resource management, meaning checking and enforcing limitations on the resources used by the software components put up on them. Also, maybe virtualizing the machine, which has its advantages. Get to that later. But also abilities to stop executing the software components, which is pretty important for a dynamic system. Going into the related system sections. So most probably all of you are pretty aware of how you can run Java code from somewhere. So somewhere, maybe the operating system, Well, you put a JAE in there, you call that from CLI, you're done. Or you build a native executable from that using our Jamaica builder or our pre-built Jamaica AMS, using Jailing, or using a GraalVM native image and calling that as for any other native process. You can embed that into your C code, means calling the operating system to start a JVM, or from C code you have the nice possibility of doing what I call reverse JNI. Actually, it's JNI, creating a VM from inside JNI code with a JNI create Java VM call. If you do something else, like Python, for example, you basically use the means that I quoted before, and there are even libraries that use the means quoted before that makes the job easier for you. Same for Docker. You can use all the means quoted before. And then there are pre-built Java containers nicely listed in the top before. We have a special category on here, which is the ICA's sugar to it. For real-time and embedded OS, you usually not necessarily find a Java runtime that is capable of running there due to limitations, some kinds. Of course, there are competitors of ours, which aren't named here, but for those operating systems, we are there providing the same means as you would know them from a regular Linux. Next slide is a little tricky, since you have to read it the other way around. So now we want to access native artifact software components from inside the Java application. How would you do so? Well, assuming we are talking about operating system libraries, native libraries, libraries that are precompiled, you could use JNI, JNA, JNR, usual Java mechanisms. Nobody likes them, but they are there. You could use the process API, which is the classes process builder and related. Or there are also specific wrapper libraries, again, which to a good part use JNI, but hide it under the hood. Pretty much the same goes for script files again, but there are some more interesting approaches to that. So again, using the example of Python here, you have a JSON library which would execute Python on Java, or you could use the polyglot quality of GraalVM, the truffle framework, to actually execute Python code on your GraalVM. Now you are in a Java application, you want to control or address a container, again, Docker, for example. There is an integration of Docker in EclipseCon that uses a Docker Java library, which is the only one I really found in use. There had been another library from Spotify, actually, which is called Docker Client, doing the same thing. You could just use the Docker API as somebody did before, or speak to the Dockerd, so the Docker command line interface directly. When speaking about specialized hardware, and I targeted FPGAs and GPGPUs here, you usually have a library for that, a specific library. But you also have some abstraction on operating system level by the standards of CUDA and OpenCL. And what we did is kind of develop Java services that use the means that are already there to update components in FPGAs and GPGPUs from inside Java. And there is a second approach, which is called a Tornado VM, trying to run Java code on specialized hardware. So there you really would describe the functionality you want to put onto your FPGA, your GPGPU in the Java language. And last but not least, if you have further systems that may be attached to your system, the system running the OSGi stack in a gateway system, There's nothing else in specific wrapper libraries that is kind of the debugging connection or the bootloader connection to the external hardware device. Into managing software, listing the runtimes again that are in my focus here, plus their interfaces and the software components managed and the containering around that. So that I assume is no magic, so I will just quickly skim through it. So yeah, there's everything from going bare metal, which then is just a block of memory, as a container, which is managed in form of e.g. an OS image, which then is put to a specific driver by either programmatic or command line access. There are operating system mechanisms for updating software on the operating system. What could be of interest there? Obviously, there's OSGi for OSGi bundles. And yeah, if you speak of container runtimes, the component usually consists of two parts, which one is the image that describes the container, and the instantiation of the image then is the container itself. Inside the container, you usually find something that looks like an OS or is part of an OS, and that is what you would code against. Now, if we want to manage such a runtime next to our runtime, which is an OSGi runtime, the common challenges are, well, how to speak with it. I want to update something. Is it something actually the piece that I want to update? And if so, is it completely downloaded to my system where I want to update it? Maybe I want to check who has created the component I want to update to make sure that it's a valid and authenticated component for the system. Then obviously the component needs to be executed in a fail-safe manner. And although the update needs to be executed in a fail-safe manner, that means the managing instance needs to check whether the update was successful, even if possible, even whether it was effective, so whether the update actually performs what it is expected to do. And therefore, you need mechanisms to kind of undo the update and have that in a transactional state without the system losing its functionality in between. And last but not least, there are certain implications when you leave the secure sandbox of Java. I will now dig into the single topics. So what we did is kind of build a stack that looks similar to this. I'm pretty sure I have a red dot here. So assuming we have some kind of embedded target device, does not really need to be embedded, but for the sake of explaining, embedded target device, where we will put our OSGi stack onto it. So we have a Java runtime down here. We have an OSGi framework on top of it with a set ICA's special sugar in it. We built all of this into a single binary. That is why I labeled it twice as an operating system software component here. And the niceness of this bundling is that we do not need to adhere to the closed world assumption we had before in GraalVM. That's actually the distinctive factor between Jamaica VM with its builder tool and GraalVM still, that we actually can dynamically load code after having built a native executable. Even more so, we introduced a tool that would ahead of time compile OSGi bundles before dynamically loading them, thus regaining the performance and the operating system compatibility of a native executable while still having the dynamic update capabilities of OSGi up there, And then, as said, introducing a control plane by the product we call EDP, which is pretty much remote OSGi, with the exception that we have this server up here. So we follow a strategical principle that says we do not want to have any inbound connection on the target device, but the target device will call out to its server to do all the management. There's obviously a nice web user interface on top of here, addressing different users and different roles. The topic of this talk is how to connect that to, e.g., a Docker container running next to it. And this, not having said that this wouldn't run in a Docker container, so obviously that this guy here could be a Docker container as well. So when speaking about Docker, we will always have a runtime underneath, which itself is a software component for the runtime that is called the operating system, which itself is a software component for the runtime that we would call the bootloader, but that's side topics. As said, we want to manage the component that sits in here. How would we speak to that guy? So what we do and did, and what EclipseCon did before us, is actually connecting to Docker by one of the ways quoted before. Meaning we have driver bindings for Java and OSGi services. Meaning there's a nice API that uses the tools that Docker provides. Here it's RESTful API and or the Docker daemon to start, stop, install, manipulate, even download Docker images from the Docker registry. And then the hardness in this is linking that up with the OSGi lifecycle. So we want, and assume all of us would want, to have an OSGi bundle which reflects the status of the Docker container, so that we can actually just wrap that stuff into an OSGi bundle, put it down here, have an OSGi bundle, represent the status of the runtime. And then last but not least, the third bullet point I mentioned in here is pretty important to us. So we have a virtualized runtime here. We do have a virtualized runtime here, which is pretty nice for the system, because this will not be able to brick the system. This will not be able to brick the system. And if you apply resource budgets to both of them, exclamation mark, both of them, you can give hints to the operating system scheduler that guarantee that the control plane will never be stopped from running, e.g. by distributing cores, e.g. by limiting CPU, memory, or number of threads for Java as well as for outside Java. Then we use the features that are readily available in OSGi and Java security to validate the completeness of the transmission of the bundle by validating the checksum that comes with a manifest, and doing the authentication that is provided by Java security, which makes us obviously pretty critical when it comes to deprecating the Java Security Manager in current versions. So either we would need to introduce a different concept or really see how we get those features which we assume are mandatory for a secure system implemented in this scenario. Then you can nicely use the dependency resolution in OSGi to manage those things, as well as any dependencies that come with installing your application here. So maybe you have an OSGi bundle that communicates with the contents of the image that you can nicely link using the OSGi mechanisms. And then our framework would actually check the resource and API restrictions before admitting a bundle to run in the OSGi system. what is required for actually linking the lifecycle and reporting execution status? Well, we connect down here to the operating system. We do a good lot of watchdogging, checking the status in the operating system, and that is really using the operating system tools to get information about what processes are running. We extended that a little to what is available inside Java. And then there's a nice agent or client or agent tries to actually react on the status it perceives. So there are some actions that it can apply itself if desired by the user, like restarting something here. If it isn't there, shut down. Maybe it's not desired, then it doesn't do anything but report up here, so that you have a reflection of all the OSGi bundles and their status, as well as the external components and their status. I already mentioned that briefly. There are certain implications if you now think of removing the Docker underneath and going bare metal. So if you remember the big table I put on there, there were several methods for actually calling non-Java code from inside Java. The problem with that, obviously, is that you lose most of the features that the nice sandbox that Java Spence provides to you. Means you have all the risks for memory safety and process isolation that you have to be aware and take care of again. Obviously, that, if badly written, can brick your system. Since we assume that the system I displayed is deployed remotely, that means somebody needs to push a button on the system to restart it, because even all the remote management tools would stop working again if badly designed. So we try to uncouple processes from Java, even when us, and we do that a lot, use native means. We always try to keep them in a separate process, that the operating system at least can deal with them, and then introducing a communication layer. Ideally, and that's what the beauty that containers provide there, you can put some resource limits on there. You can also put resource limits already on native processes on, e.g., a Linux system by using concepts like the C groups in there. And obviously, Docker provides runtime options, which it enforces to its containers. And then, now that we have this nice system running, our current investigations go into the direction of how to make those things communicate on a standardized basis. So if you have followed the train of thoughts, you will recognize that we have communication from here to the runtime, but there actually is no way of communicating in there if this software component is not aware of what communication channel to use. So the interesting topic is how to bind or provide an API, e.g., into the Docker world that can be used for this component to make use of, e.g., an event manager in OSGi, or also the service registry of OSGi, means propagating services from out there in here in a standardized way. And frankly, I haven't found a clever answer to that question yet. That is also why this is the end of my talk. I hope you could take some news from the technologies presented, but also from the technologies that we have put in place here that inspire you or make you interested in our solutions. And last but not least, pointing to the talk that will follow up here, focusing on the aspect of the real-time features of this relation. I think it's due at 4 p.m., James, isn't it? 2:40? Well, 2:40. Opening the table for any questions.